everybody. Our objective here is to really understand energy profiles in terms of enthalpy, exothermic and endothermic, and chart them and understand what it's telling you. All right. Remember, an energy profile diagram is where you're charting potential energy and your reaction coordinate. And the reaction coordinate is like what the molecules do, what they look like. And they look like these are what the profile diagrams are. All right. Something like this. This would be exothermic. Okay, for our first reaction, we're going to react some concentrated acid, 3 molar acid, and we're going to react it with concentrated base, right? A neutralization reaction. And we're going to see what happens, all right? Okay, this is the potassium hydroxide that's in there. I'm going to add the base, or the acid, hydrochloric acid, all right? And you can see there, it's pretty clear the temperature's going up. You can see it rising, all right? All right, now what was the reaction that we saw? Well, we reacted potassium hydroxide with hydrochloric acid, and we made potassium chloride and water. All right, now these are both, this is a strong base and a strong acid, so they're both strong. They're both going to dissociate, and this would be what they're going to dissociate into. You notice my potassium and my chlorines, they're going to fall out. So my net ionic equation is this. So now, as you saw, the the temperature went up. So my reactants had some kind of uh, energy, and my products would have had less because I saw temperature being released. And this is potential energy, PE, and this is my reaction coordinate. All right? All right, so an exothermic reaction profile, you got your potential energy. That's going to be measured in kilojoules per mole. You got my reaction coordinate, and it's going to go up and then back down, much like this. All right? And my reactants start here. They've gotten a certain amount, but my products have less because of this distance. This is my delta H, and it's going to be negative because my delta H system is equal to my energy of my products minus my energy of my reactants. All right, that's my delta H system. So this is going to be equal to a negative kilojoules per mole. All right, that got cut off. And that's what this would be. So yeah, it goes to there. And this distance here is your activation energy. Now, in this this reaction, this is important. The surroundings is the water, is the solvent. All right? And the system is it's kind of like your potassium hydroxide and the HCl. All right? The molecules in there are the system, and I should have, I'll do 2 dots, 2 different things. And even more specific, it's the hydroxide and the hydronium and the hydroxide are the system, and they're releasing that energy out into the surroundings. We're measuring the temperature of the surroundings of the entire thing. All right, and that's what's going on in terms of that. That's an exothermic reaction. And with an exothermic reaction, our enthalpy would be negative. It's releasing energy into the surroundings. It's kind of fun. It feels warm. All right. The surroundings, like the test tube itself, the container, it feels warm. All right. Exothermic. Okay. For our next reaction, we're going to do some citric acid and some baking soda. All right. I've got my citric acid in a little beaker, and here it is. And you can see that's its temperature, right? Around the same temperature as before, the one before it. And what we're going to do is we're going to dump some baking soda in there and chart what happens to the temperature. See what happens. Okay, here we go. All right. All right. Okay. You saw temperature was around 18 or 19, a little bit till 20, and then it went down. So, endothermic reaction. Now, this is also an acid and base reaction, but you'll notice it's making a gas at the end. The gas it's making is carbon dioxide. It takes energy to make to make the gas. Where does that energy come from? It comes from the surroundings. All right. I'm reacting and citric acid and baking soda. They come together and they're like, whoa, we want to make this gas bubble carbon dioxide. Where are we going to get the energy to make this bubble? We're going to suck it in from the surroundings and make it. Therefore, it's an endothermic reaction. Okay, this is acetic. Sorry, if I had said acetic, it's citric. It's not acetic prior. I've been using a lot lately and so citric acid, all right. I add solid sodium bicarbonate. There's a three there. I produce carbon dioxide, that's the bubbles. Produce some water, and then I produce the salt, sodium. And this anion, I'm not exactly sure what it is. This is a uh, acid, and this is its conjugate base of citric acid. All right. So this clearly took energy because the temperature went down. So this, you'd put the energy in the equation. You'd put the energy over here. It'd be like energy plus this yields these things. Okay. Oh, energy plus this yields these things. Now, the net ionic equation isn't going to look much different because the only thing would be this would be dissociated. Um, but that's uh, that's the overall equation. Now, think of this is there's some elemental steps going on here because this is four molecules here. So we're not going to get into that. This is just the overall equation. All right. What's that energy profile going to look like? Okay, what's this reaction profile going to look like? It's going to look like this. Key thing here is in terms of enthalpy, I know we've seen these profiles before. My penthalpy is going to be positive. Uh, this distance is my activation energy. This distance represents my change in enthalpy, and you'll see that it's positive. You always take your products minus your reactants. And in this case, the energy of my products is greater than my energy of the reactants. So my delta H would be positive. So when I minus them, 5 minus 2 would give me 3. I'm going to have a positive kilojoules per mole. And the system draws, great word, great verb there, energy from the surroundings to happen, to do this. Now, uh, that's how this reaction occurs or how it occurs. That's what this means in terms of uh, enthalpy and the reaction profile. And this one would be considered unfavorable. All right. And because you need energy to do it, therefore it's unfavorable. And the products are less stable simply because they've got more energy. In science or in chemistry, the more energy, the less stable. All right. So products are less stable. And by reverse, the exothermic, if you could add this is favorable and products more stable. All right. And that is the two different reaction profiles for uh, in terms of enthalpy. All right. One's got a negative delta H, one's got a positive delta H. All right. Thank you. Hope you're well. Bye.